Hey everybody. Today we're getting into logarithms. We'll talk about what they are, what they look like. We will talk about their properties and we'll solve some equations with them, all the good stuff. First of all, the definition. Y equals log base b of x means x equals b to the y. So we're defining the logarithm with base b in terms of something a little more familiar, an exponential function with base b. Remember that exponential functions are required to have a base that is positive and not equal to 1. We keep that requirement when we start talking about logarithms. When you see log base b of x, you should be thinking b to what power is x. If you keep that in mind, solving arithmetic questions with logarithms gets to be pretty easy. For example, log base 5 of 125. I'm asking 5 to what power is 125? And the answer is 3. 5 to the third is 125. A slightly harder one. Log base 3 of 1 over 81. I'm asking 3 to what power is 1 over 81? Well, I know that 3 times 3 is 9, times 3 is 27, times 3 is 81. So 3 to the fourth is 81. To put something in a denominator, I need a negative exponent. So 3 to the negative fourth is going to be 1 over 81. So the log base 3 of 1 over 81 is negative 4. One last computation problem, log base 4 of the square root of 2. 4 to what power is the square root of 2? So I want to take the square root of 4 and then the square root again. So it's 4 to the 1/4 is the square root of 2. So log base 4 of the square root of 2 is 1/4. Let's talk about the graphs of log base b of x. Depending on whether b is greater than 1 or whether it's between 0 and 1, the graph is either going to be increasing or decreasing. Either way, you're going to get a vertical asymptote at x equals 0, and you're not going to have a horizontal asymptote. The graph will either increase without bound if b is greater than 1, or decrease without bound if b is between 0 and 1. You can also see the domain in each case, always just positive real numbers. Conversely, the range is going to be all real numbers. The fact that the domain of the logarithm function is the positive real numbers allows us to solve some problems with where we're finding the domain of more complicated functions. Like this example. G of x equals log base 10 of x squared minus 2x minus 8. We want to find the domain here. So we know that the inside of that logarithm has to be positive, strictly greater than 0. So we need to solve the inequality x squared minus 2x minus 8 greater than 0. The way we're going to do that is by finding the cut points, the place where that left-hand side is equal to 0 or where it does not exist. And then we're going to make a sign chart. So let's set that left-hand side equal to 0, factor, and finally get the answer, x equals negative 2 or x equals 4. So that's where the function on the left there is equal to 0. We need to know where it's positive, where it's negative. So we're going to make a sign chart and test points in each of the intervals between 4 and negative 2, and on either side of those 2 points. So here's the sign chart. I've labeled the 2 cut points, x equals negative 2 and x equals 4. Now I want to take a point to the left of negative 2, a point between negative 2 and 4, and a point greater than 4. Plug all of those into the function, see whether I get something positive or negative. When I plug in negative 3, into x minus 4 times x plus 2, I get a positive value. It's going to be a negative times a negative. And therefore, this function x minus 4 times x plus 2 is going to be positive on the entire interval from negative infinity to negative 2. Similarly, I plug in x equals 0. I get a negative value back. And I conclude that x minus 4 times x plus 2 is negative from negative 2 to 4. Finally, I plug in a value larger than 4, like 5, and I get a positive times a positive. So x minus 4 times x plus 2 is going to be positive from 4 to infinity. Overall, x squared minus 2x minus 8 is positive from negative infinity to negative 2 and 4 to infinity. So that's going to be the domain of log base 10 of x squared minus 2x minus 8. There's lots of useful properties for logarithms. The first two that we should look at are the cancellation properties. Basically saying that logarithms and exponential functions with the same base undo one another. Log base b of b to the x is x. for all x's, because I can plug any x into that top function that I want. B to the log base b of x is x for all positive x. That just reflecting the fact that the domain of log base b of x is just the positive numbers. So you should always bear in mind the simple sentence in regular language: exponential functions and logarithmic functions undo one another. That's really useful when you're solving equations. Here's a simpler example. We'll do a more complicated one later on. Find x if log base 2 of x is 5. So I know that 2 to the power and log base 2 are going to undo one another. So I'll take 2 to the power on each side. The 2 to the power log base 2 of x, that's going to undo. Those functions are going to undo each other. The left-hand side is x. The right-hand side is 2 to the 5th, 32. For every law for exponents, there's a corresponding logarithm law. So there's 3 in particular that we really need to know. The logarithm of a product is the sum of logarithms. The logarithm of a quotient is a difference in logarithms. And a logarithm of something to a power means you can take that power, in this case r, and pull it out and make it a factor out front. It's also worth remembering that log base b of 1 is always 0, b to the 0 is always 1, and log base b of b is 1, b to the 1 is b. One quick example using these logarithm laws. Log base 9 of 27 plus log base 9 of 3. They're the same base, so using property 1, I'm going to combine those two logarithms. It's a sum of logarithms, so I'm going to write it as a logarithm of a product. I get log base 9 of 81. And this I can evaluate using the definition of logarithm. I'm asking myself, 9 to what power is 81? And the answer is 2. Let's do a few problems practicing the laws of logarithms. In each of these problems, we're going to try and write the expression using just a single logarithm. Number 1, 3 log base 6 of x plus log base 6 of y minus 4 log base 6 of z. So first of all, I'm going to use the fact that if I have a number times a logarithm, I can take that number out front and make it an exponent inside. So for example, 3 log base 6 of x is log base 6 of x to the third. Similarly, 4 log base 6 of z is log base 6 of z to the fourth. Next, I'm going to take those first two logs, a sum of logarithms, and combine them, recognizing that a sum of logarithms is a logarithm of a product. Finally, now I have a difference of logarithms, so it's going to be a logarithm of a quotient. There's my final answer. Problem 2. 5 log base 2 x plus 1 minus log base 2 of x squared minus 1. Again, I'm going to use that exponent rule. I'm going to move the constant factor of 5 inside the logarithm and make it an exponent. Next, since I have a difference of logarithms, I'm going to make it a logarithm of a quotient. Log base 2 of x plus 1 to the fifth over x squared minus 1. Now, of course, x squared minus 1 factors as x plus 1 times x minus 1. So the last thing I'm going to do is to cancel that factor of x plus 1. Overall, log base 2, x plus 1 to the fourth over x minus 1. The logarithm laws and cancellation properties, when you take them together, you get a powerful toolkit for solving equations involving exponential and logarithmic functions. So for example, log base 2 of x plus 2 plus log base 2 of x minus 5 equals 3. So let's combine the left-hand side into a single logarithm, log base 2 of x plus 2 times x minus 5 equal to 3. And then let's use our cancellation property. Let's take 2 to the power on both sides. The left-hand side is going to be x plus 2 times x minus 5, and of course 2 to the third on the right-hand side is just 8. Now I just need to solve this. It's just a regular polynomial equation. My approach is going to be to move everything to one side. So I'm going to FOIL out the left and subtract 8 from both sides. X squared minus 3x minus 18 equals 0. Factor that. X minus 6 times x plus 3 equals 0. So x equals 6 or x equals negative 3. You have to be a little careful on problems like this. Notice that negative 3 isn't in the domain of either of the original logarithms. When I plug in negative 3 to either one of those, I'm taking the logarithm of a negative number, which isn't allowed. The thing that happens here when I use the logarithm going from the first line to the second line is that I am then doing the logarithm of a negative times a negative. So I have allowed an additional answer, a sort of phantom answer, to creep into my work. Bottom line, when you're solving equations with logarithms, it's a good idea to check your work at the very end. We have one special exponential function, y equals e to the x. Accompanying that is one special logarithm function, the natural log, y equals ln of x. Y equals ln of x just means x equals e to the y. We have cancellation properties, of course. The natural log of e to the x is just x for all x, and e to the ln of x is just x for all positive x. So those are just the same cancellation properties we saw earlier, just written in terms of natural log and e to the x. In particular, you should remember that the natural log of e is equal to 1. The natural log gives us one more important property of logarithms, the change of base formula. Log base b of x equals ln of x over ln of b. It's actually possible to write the right-hand side using any base logarithm, but the only time it's ever practical that I've ever seen is using natural logs. This one does occasionally come up, particularly if you need to do a problem where you need a decimal answer using a hand calculator. For example, log base b of the exponential number e is the ln of e over ln of b, so 1 over the natural log of b. Example 2, log base 2 of 9. Most calculators don't have a log base 2 button, so if you need to do this in a calculator, you're going to need to use a change of base formula. ln of 9 over ln of 2. Your calculator probably does have a natural log button, so you can put in each of those things, get these decimal approximations, and divide to get about 3.17 in this case. Let's wrap up by doing one harder problem that's going to use a bunch of the properties of logarithms we've talked about in this video. Let's solve 5 to the 3x plus 2 equals 4 to the 1 minus x. So I've got two different exponential functions, one on each side, and they've got different bases. So I'm going to take natural logs of both sides. This is helpful because now I can use a logarithm property to bring those exponents outside. 3x plus 2 times the natural log of 5 equals 1 minus x times the natural log of 4. A bit of a mess, but if you remember that natural log of 5 and the natural log of 4 are both just numbers, the way to proceed is fairly clear. You're going to FOIL those numbers through. On the left-hand side, I get 3x ln of 5 plus 2 ln of 5. And on the right-hand side, ln of 4 minus x ln of 4. Next, I move everything with an x to one side, everything without an x to the other. Factor out that x, and divide to get x all on its own. Technically, we've solved the problem. We have x equals something. Here, we can simplify a little bit using more natural logarithm properties. On the top, I have a difference of logs. That's a log of a quotient. And on the bottom, it's a sum of logs. That'll be a log of a product. If I actually put those numbers into my calculator, I get about negative 0.295.